Hi everyone. Today we'll talk about how to accelerate autonomous vehicle development using Amazon SageMaker. I'm Nitin Wag, ML specialist at AWS, and with me I have Alex Ben, ML engineer from Lyft Level 5. So we'll start off with typical challenges in machine learning in AV development. Then we will deep dive into Amazon SageMaker capabilities for machine learning development in AV. And then Alex will walk you through how Lyft Level 5 is using Amazon SageMaker for hundreds of their scientists. So let's get started. So autonomous vehicle, also known as self-driving vehicles, are designed to travel between destinations without a human operator. It takes an incredible amount of data processing and compute to make this happen. Autonomous vehicle development lifecycle consists of data acquisition by driving cars on the road, then massively ingesting the data to cloud at regular interval, then data preprocessing, data labeling, mapping, model training, and simulation. Today, we will only focus on machine learning for autonomous vehicle development. So there are three primary stages in machine learning life cycle for AV. First, you label terabytes of LIDAR 3D point cloud and image data, then set up and manage GPU clusters for machine learning training, and then deploy the trained model into cars for testing. Typically, machine learning users at AV includes researchers and engineers. AV testing vehicles can generate up to 20 to 60 petabyte data per year, and model training for fully autonomous vehicle requires hundreds of thousands of GPU-based servers for machine learning training. So there are several challenges in ML development for AV. For first, data labeling at this scale with terabytes of data gets complex and costly. Then setting up self-managed infrastructure requires significant engineering, so multiple teams can experiment in matter of hours, and at the same time, you have to manage cost of GPUs. And once models are ready, they need to be turned into a deployable model so they can run into hardware installed in the car. And in absence of standard platform, there's often a divide between developer environment across the teams, leading to knowledge silos. So let's see how Amazon SageMaker can help you overcome these challenges. Amazon SageMaker is a managed machine learning service adopted by many AV, ADAS, and automotive customers. It eliminates undifferentiated heavy lifting by providing on-demand capabilities to manage machine learning lifecycle for AV development. To begin with, it provides SageMaker Ground Truth for data labeling for 2D images and 3D point cloud at scale. Then users can leverage managed data preparation capability for data pre-processing, for example, image to TF record conversion. Then they can launch manage one-click model training on single GPU or multi-GPU training clusters. And once model is trained, then optionally, customers can leverage SageMaker Neo to compile model for target hardware architecture. It is a standard platform that can be leveraged by research and engineering teams and supports industry-leading frameworks like PyTorch, TensorFlow, and MXNet. Users can manage and compare, track experiments, and also profile or monitor long-running training jobs automatically. Developers can continue to use their existing IDEs like PyCharm, VS Code, command line, or Jupyter notebooks using Boto 3 or Python SDK. And customers who are using Kubernetes can also leverage open source projects like Kubernetes components for SageMaker or SageMaker operators for Kubernetes to leverage SageMaker capabilities right from within Kubernetes. So let's discuss these capabilities in depth. Based on our discussion with many AV customers, what they need is scalability, visibility, and control in their data labeling pipelines. So SageMaker Ground Truth is fully managed labeling capability within SageMaker that provides 30 plus computer vision workflows for 2D image labeling, tasks like semantic segmentation, bounding box, instance segmentation, and it also provides production-grade LiDAR 3D point cloud for object detection, tracking, and segmentation. It supports assistive tooling to increase the speed of annotation using machine learning capabilities like Dexter, interpolation, and many more. It also provides auto labeling capability to reduce cost of labeling by up to 70%. Customers can continue to use their internal teams or use 8,000 managed annotators available via AWS Marketplace, and all capabilities are pay-as-you-go with no lock-in, and customers can qualify for volume discounts. Now, once the data is labeled, next step is data preprocessing. So common practice in world of machine learning is to shuffle and process the data before training. So SageMaker Processing allows you to launch data preprocessing for large volumes of data on distributed cluster using on-demand CPU or GPU clusters. You store the data in Amazon S3, which acts as a source, and then author processing logic using Python or Spark script. You can also bring your own custom container packaged with logic and dependencies. Once you have your script ready, using one-click API, developers can then quickly launch a single or distributed processing job. And SageMaker takes care of launching on demand in cluster. Now, process data is then stored back into your Amazon S3 bucket, and instances are terminated. And you only pay for the time the processing job ran and is billable by seconds. So here's a sample example of a one-click API where you can bring your own script or container, select the type of instance, and provide input and output location. And then SageMaker takes care of launching instance using single node or distributed processing. For distributed processing, data sharding is a common technique and which is also supported, and it is based on S3 prefixes or keys. Once the data is processed, the next step in the machine learning lifecycle is training. One of the most powerful capability in AV is SageMaker Managed Training. You don't have to invest engineering time to set up and manage training clusters and use on-demand GPUs when needed for training. So using one-click API, you can use Amazon S3, Elastic File System, or high-throughput FSx for Lustre as a source for SageMaker training. And SageMaker provides you built-in containers for TensorFlow, PyTorch, MXNet, where you can bring your own script or you can just use the custom container. Using one-click API via Python or Boto3 SDK, you can then launch SageMaker training job. SageMaker handles launching the container using on-demand or spot instances, streaming your data, and it'll optionally monitor the job for conditions like vanishing gradients or exploding gradients at no extra cost. Once the training is completed, model is saved back into your Amazon S3 bucket and instances are terminated. And you only pay for what you use during the training billable by seconds. Now you can also use managed spot instances for training to save cost by up to 70% over on-demand instances. So here's a simple example of SageMaker one-click API using Python SDK. Optionally, you can define monitoring rule, such as vanishing gradient here. Then using estimator API, you provide your script or custom container location. Then select number of instances. Then choice of GPU like P316X large with 8 GPUs or other suitable instances in P3, P2 family. Then you can optionally use managed spot training by specifying this simple flag. And SageMaker will use spot instances for training. Then you call estimator.fit method with the source location, which is in S3. And finally, provide experiment tracking configuration like trial name, stage. So SageMaker can attach training run to a trial that can be tracked via API or visually. Moreover, SageMaker training API is consistent across all frameworks like TensorFlow, PyTorch, and MXNet, bringing standardization for machine learning training. Now with this, I would like to invite Alex Ben from Lyft Level 5 to share their experiences about SageMaker journey used by hundreds of researchers and machine learning engineers at Lyft Level 5. Alex, over to you.
Thank you, Nitin. I'm Alex, and first, I'd like to tell you some about Lyft Level 5. So Level 5 is the division of Lyft that's building an autonomous ride-sharing service. We started in 2018, so we're relatively new, but we're working fast. Right now, we're actually testing our AVs in the San Francisco Bay Area. Our service is not open to the public, but you might see some of our vehicles. If you do, they're being operated by our fleet of safety test drivers, and we're working on them. We're working on the service as fast as we can and iterating as quickly as possible. So to start off with, I'd like to tell you some about how we use machine learning with our vehicles. Looking at the screenshots, you can see some images of the AVs that we're building. On the lower left, you can see the kind of sensors that are outfitted on the vehicle. So we have, you can see the sensors below and on top of the car. Zooming in on the screenshot that's for the on the right, for the sensor rack that's on top of the vehicle, it has a number of high-definition cameras. It has radar units, and the thing on top is a high-powered LIDAR sensor. So these sensors are what feed into our machine learning models for perception, prediction, and planning that I'll tell you about in a second, and ultimately feed into our machine learning models and help the car decide how to drive. So since you're interested in this talk, I'm sure that you must be interested in AVs, and you've probably seen some videos online about other companies' AVs, or perhaps the Tesla full self-driving beta. But it's always fun to look at AVs in operation and look at how they use machine learning to drive on the road. So let's take a look at some screenshots of our vehicles. So this first image is about how the car collects and processes the LIDAR sensor data that it uses is one of the signals that it uses to get information about the world. So if you remember, the LIDAR is a sensor that's on top of the vehicle, and the way it operates is it sends out beams of light in every direction. And so those are represented by the concentric circles in the image. Those reflect off elements in the world and are collected back in the sensor and feed into our machine learning models. And what you see in the screenshot is a visualization of the reflections of things that the LIDAR perceives in the world. So now let's take a look at our actual AVs in operation. So looking at the screenshot on the left, this is the driver's view, looking out through one of our AVs, which is operating in autonomous mode. You can see the Bay Bridge on the back in the background. So this is driving in San Francisco. Now we're driving along and we see cars in the world. On the other lane, a couple of buses pass. And now looking on the right, this is the view of how the AV is perceiving the world. And we call these models our perception stack. So these are machine learning models. They're about detecting the cars, pedestrians, cyclists, traffic signs, stoplights, drivable surface areas like the lanes, all the elements in the world that the AV needs to really perceive. You can see in the screenshot that the blue boxes represent the vehicles, and you can see the vehicles in front of us. You can see a bus pass by on the left if you're quick enough. A stoplight will come up, and there's no pedestrians in this screenshot, but you would see them with highlighted in a different color. Now let's turn to a different class of models beyond perception. The next one is about prediction, specifically motion prediction. This is a very different screenshot, and focus your eyes on the screenshot to the left. So what you see in the middle is the red square is our autonomous vehicle. Now you can see it's driving on the road, and the lines obviously represent lanes. The yellow squares are the motion of other vehicles on the road. We would also capture pedestrians and other elements, but this is just vehicles. And this information, it feeds into our machine learning models for prediction. So what's going on here is that as the car is driving, it's recording the motion of the paths taken by all the other cars on the road, or other pedestrians or cyclists, or other elements on the road. And we're going to feed that information into our prediction models. As the car is driving, it's constantly making predictions about where all the elements on the road will be over the next few seconds, and using that to understand where their motion will be. Taking these two models together, they actually feed into our third class of models, which is planning. So planning really is where everything comes together and the rubber meets the road, so to speak. Planning is all about how the car decides where to drive, decides which lanes to drive in, how fast to go, whether to stop, accelerate, and so on. What's going on here is you can see the AV just passed this stop car that was ahead of it, which is kind of the red car, and you'll see it again in a second. Now, it needs to use its perception models to understand what are all the cars on the road or other elements on the road, such as stop signs, traffic lights, people, the lanes, and other things. Then it feeds that. Then it uses the prediction models to understand that this red car in front of us is likely to stay stopped. And finally, the AV realizes through planning that it needs to do something about it. So what it decides to do is nudge around it to the left, and it makes the decision that it has just enough information to pass safely around the red car to the left, and without interrupting, without any risk of hitting any other cars around it, and continues on its way. So between perception, prediction, and planning, this is really the core of how our AVs decide to operate on the road. And this is all pretty exciting to do, pretty innovative, especially for a machine learning engineer. But honestly, I want to turn to the life of our engineers from day to day. And that actually is no different from any other machine learning organization or team. This is how we do things. We gather data that comes off of our AVs, which is basically images, video, and motion of other vehicles collected from the time the AVs spend on the road. We send some of that information to a third-party annotation service. So, for example, a human annotator will look at a video, draw bounding boxes on where all the cars are, and that becomes ground truth information that our machine learning models will use to understand which parts of the video or images are cars. Then we train models, which today we use PyTorch. I'll tell you some more about that in the next slides. But we're iterating on our models to improve them. Sometimes we're starting new models. We take those models and next we deploy them in simulation. So we want to understand in a simulated environment how well our models might perform as they drive throughout the world. And we take our best models, we deploy them to our car, we test them through the San Francisco Bay Area, and we repeat this process day after day, week after week. So now I want to turn to, from the actual system side, what we're doing to run this process and train our models. So at first, not surprisingly, what we did is we started with workstations with GPUs that we bought at the store, put in our workstations, started training TensorFlow models. Obviously, this only would scale us to a certain size, just as much data and complexity as could be fit into a workstation. So what do we do next? Well, we built a cloud Kubernetes cluster consisting of EC2 instances running in the cloud, and we enabled our users to start using it to train models. Kubernetes is definitely complicated. It's complicated to operate. It's complicated to use, but our users were able to start training models. What they did is they picked a powerful GPU instance type, started using it to train, they added more data to it, they increased the complexity of the models, and eventually training began to slow down. So we went to the next most powerful GPU instance type. The training was faster again, and they started adding more data and increasing the complexity of their models. And we had the same problem. And very quickly, we arrived at the most powerful GPU instance type offered by AWS at the time. And the same thing happened, and model training slowed down from hours, actually to a day, and then actually to multiple days to train our computer vision models. Users became overall frustrated with the complexity of working with Kubernetes and the slowness of training of their models. And so I got involved in depth. I looked at one of our models, and actually I found the first couple of hours, all the model did was spend time downloading data from the cloud to use for training the model. I spent a lot of time to improve the data pipeline and improve the training efficiency of the job, and that worked. But we have dozens of models, and the approach just wasn't going to scale to all the training that we were doing. So I began to realize that we needed to make a major change in how we were operating at level 5. At about the same time, my team and I were doing a prototype with Amazon SageMaker. So we were attracted by the fact that SageMaker is a service that's completely managed by AWS, so we don't have to run any additional cloud infrastructure to use it. All we do is we train our containers, we upload them to ECR, and we run a SageMaker custom training job, and that runs all of our training with our containers for us. So it's super easy to use, it's super easy to get started with, it's super clear for users how to use it. As part of this process, I realized that it would be really easy with SageMaker to start using distributed training. And so this just means that I can train with a single node, I can train with multiple nodes, I could train with like 8 or 32 or even 64 nodes with SageMaker. Super easy, it's just a parameter that I specify. We started converting some of our models with PyTorch, and we realized that we could use PyTorch with SageMaker together to start using distributed training super easy. Distributed training is actually built into PyTorch through its distributed data parallel class. That's a class built into PyTorch that will orchestrate all the distributed training for you. It's compatible with something else in PyTorch called distributed sampler. So what distributed sampler does is that when you run a distributed training job, you have all these nodes participating in the job. Each node will just take a small random piece of the data set and use that for training. So your entire data set is being chopped up and split up amongst all the nodes that are participating in your job. And that actually solves our data scaling issues. So now we're training with the data parallel job, and each node is just using part of the data set. So overall, we were able to use this to achieve a near linear scaling. So when, for example, if we run a job with 4 nodes, our jobs run roughly 4 times as fast as they did before. You can't achieve an exact one-for-one speed up because there's some overhead, but we're definitely back to training jobs in minutes and hours instead of hours and days. I have a couple more notes on the slide about the instance types and managed spot training that we're also using, and I'll come back to that in a little bit. But this is the actual impact of what happened when we started using SageMaker. So at the beginning of this year, we decided to go all in on SageMaker and PyTorch together with distributed training and start doing this for all of our machine learning models. So my team is just myself and a couple of people, and we have at least 100 engineers every day training all kinds of models using SageMaker. And essentially from a support perspective, since it's a completely managed service, we spend very much time on the support aspect. Since there's not additional cloud infrastructure to operate SageMaker, we have no additional infrastructure overhead or costs associated with operating SageMaker. It's all handled by AWS. For users, since they can scale to their data and train on multiple nodes, they're back training models quickly in minutes and hours. And the surprising aspect is that since our training efficiency is just so much better than it was when we were using Kubernetes in the previous year, that we're actually spending less money, much less money, for all of our machine learning with SageMaker, even though we're now training 3 times as many models as we were with Kubernetes. So finally, I want to share some of our technical conclusions about distributed training for deep learning. So this is kind of like some hardcore knowledge for machine learning system engineers. This first one is actually just my opinion, and it's about if you're starting a new deep learning project, I suggest you use PyTorch rather than TensorFlow. So when PyTorch really first came out, it was actually much easier to use than TensorFlow. Although recently in the TensorFlow 2.x series, they've adopted a library called Keras as one of the primary APIs for TensorFlow. And they have a mode called eager execution. And between these things, you can basically do anything with TensorFlow that you could do in PyTorch. However, it's still true that from your mental overhead, it's still just a little bit easier to do things with PyTorch than TensorFlow. So if you're starting a new project, I would start with PyTorch. If you already have experience with TensorFlow, then it doesn't matter so much, and you could use either and accomplish the same thing. You might have heard of a project called Horovod, which is about distributed training. It came out a few years ago. It introduced an algorithm called ring all reduce, which is an efficient algorithm for distributed training. And it used actually an old library called OpenMPI, which is a highly scalable network communication backbone. What I want to tell you is that these innovations have now largely been incorporated directly into PyTorch and also in TensorFlow. So if you want to get started with distributed training, you don't need to use Horovod. Just get started with PyTorch or TensorFlow directly and use that. It's still true that if you want to train the largest distributed training models, like if you want to use 64 nodes or 128 nodes, that Horovod with OpenMPI still has a bit of a better scaling factor than PyTorch distributed training, but most of us won't be training models that large. So just use TensorFlow, PyTorch to start with. And if you want to get started, I suggest you download an open source project called PyTorch Lightning, which just makes it really convenient to work with PyTorch, and it's not too difficult to hook up to SageMaker. So now we're going to go into a short demo about how we use SageMaker custom training jobs to train models every day at Lyft Level 5.
Now I'd like to give you a quick demo of how we use SageMaker at Level 5. As you heard during the presentation, we use SageMaker custom training jobs to run Docker containers. So for this demo, I wrote this short Docker container. You can see that it's a PyTorch container, and it's going to train my custom image classifier that I wrote. We actually have a lot of PyTorch tools at Level 5, and if you'd like to learn more about them, we have some great open source blogs. But for this demo, I'm just going to use this example container. If I build it, I can run it easily in SageMaker by using the AWS CLI and to run a command like this one. This will work just fine. And if you try SageMaker at home, you'll do something like this. And one of the things you'll see is that this command actually takes lots and lots of arguments, some of which are related to infrastructure settings like the network configuration, security groups, and so on. Not all of our machine learning engineers would know exactly how to specify these settings correctly. So what we've done to make it a little bit easier to use SageMaker is we've actually written our own command line interface that just wraps the AWS command line interface. It applies a standard configuration for a lot of these parameters. It just makes it a little bit easier to use SageMaker. So what we have our users do is we have them write a short YAML file with some of the configuration parameters for their job, like the GPU instance type that they want to use, how many instances they want to use. So one here means a single node training job. Runtime parameters that are relevant to their machine learning model, like the number of training epochs or the learning rate. And then when they want to run the job, they run our command line interface with a command like this one. What it will do is build the Docker container, push it to ECR, apply the standard configuration parameters to the job, submit the SageMaker training job, and give you back a link to the job. So now you can see those things go by, and so you can see first it's building the Docker container. Here it is, pushing it to ECR. It submits the job to SageMaker, and at the end, you get a link back to the SageMaker job like this one. And if I open it, I'll get back a page to the SageMaker job. So here's a version of the job that is completed already that I ran just a little bit before. You can see back all the configuration parameters that we applied for the job. Here's the runtime parameters. There's also helpful system graphs for things like all the CPU memory and GPU utilization. See, basically what happened is the job started and then these things all went straight up. And since it's just an example job, it just ran for a few epochs. And so they all ended after a short period of time. And then I've got the links to SageMaker to CloudWatch logs for the job. Click through and I go into CloudWatch. Boom, I get the logs for the job right away. And the logs basically show up almost in real time as the job executes. It's easy to filter them, and all these things together just make it really convenient for our users to work with SageMaker. We also use some third-party experiment tracking software that I'm not going to show here today, but this really captures the basics of what our users do on kind of like a daily basis. Thanks for letting me show you this demo.
Thanks for watching the demo. So I want to end with some of the lessons that we had from the past year. The first one is that we just stayed super focused on making it as easy and fast as possible for our machine learning users to train models. We didn't worry too much about get too enamored with a particular cloud technology. We just stayed focused on the models. And for us, that meant adopting SageMaker. For you, it might mean something else. But the overall effect on our organization has just been a massive increase in the efficiency of the productivity of what our machine learning users are doing. The next is that we've benefited massively from the fact that SageMaker is a completely managed service. So there's very low support costs, there's no cluster overhead, and it's simple for users to understand and use. And the last one is that we've benefited in unexpected ways. So for example, the SageMaker, there's always new instance types, new features being added every few months, and we benefit from that because we use SageMaker. And finally, I'll mention that we use spot instances with SageMaker to reduce our costs. So this is an instance type where you accept that there might be some delays in the job starting, or that a few jobs might be interrupted and restarted later by AWS. But in exchange, you can get a discount between 40 and 70% on your job costs. And we use that to really reduce our machine learning costs. So on behalf of Nitin, I want to thank you for joining us today. I hope you enjoyed our talk and that you got something from it. And please have a great rest of your day.